So let's move on to potential energy operators. Quantum mechanical operator that corresponds to the potential energy is a multiplicative operator. So it simply multiplies the function by the classical expression that defines the potential energy as a function of coordinates. You've heard of kinetic energy being energy due to motion, right? Potential energy, we say, is energy due to position. So in the classical expression for potential energy, you'll have a function of coordinates. So all you have to do is replace each of those coordinates by a coordinate operator, and all it does is really multiply. It just multiplies the function it's operating on. Okay? So here's an example. Let's assume that there are no forces acting on the particle in the system. If there are no forces acting on the particle in the system, then you say the potential energy is constant. Let's try to understand why that is. What does it mean when potential energy is constant? If you leave your system alone, okay, kinetic energy plus potential energy would be constant, right? If your system is all alone by itself, its total energy remains constant. Law of conservation of energy. So potential energy and kinetic energy are constant. The total is constant, right? So what happens if potential energy is constant? Then the kinetic energy is also constant, right? And if the kinetic energy is constant, that means it's moving at constant speed, constant velocity. It's not accelerating. So that means what? Acceleration is 0, right? What's the force on the object? The net force is 0. So that's what we mean. If there is no forces acting on the particles, you say that the potential energy is constant. Now, as a matter of convenience, we can take this constant as 0. There's really no absolute scale for energy, so we can define any arbitrary value and then define everything with reference to that. So we can just take that as 0, for example. So we can define, for example, in this particular case, our potential energy operator, this we have right here, as a function, as an operator that multiplies a function by 0. Okay, so when you do that, then what you're doing is you're just saying that the potential energy is constant, it's 0 in this case. Okay, so that's a potential energy operator. Here's an example. Let's say you have a 2-particle, one-dimensional harmonic oscillator. Okay, and that would be 2 particles constrained to move along the x-axis. You have an x-axis, and you get 2 particles. Okay, so that the interaction, the potential energy of interaction between them is given by this expression, 1/2 kr², where r is the distance between them. Okay, and the distance between them is what? Let's say particle 1 is located at x1, particle 2 is located at x2. What is the distance between them? Absolute value of x2 minus x1, right? Okay, so absolute value of x2 minus x1, that's your distance, that's your r, right? So what is r²? So r² is just x1 squared. So it's going to be 1/2 times the constant times x2 minus x1 squared multiplied by the function. Okay, so the potential energy operator is just an operator that multiplies whatever it's operating on by the expression for the potential energy. Okay? So this is the interaction between the 2 particles and no other sources of no external forces, no other sources for potential energy besides the interaction between the 2 particles. Let's look at this one right here. We have 2 electrons, electron 1 and electron 2. What's the potential energy of interaction between 2 charged particles? Remember from physics? Coulomb's law says the force between 2 particles is what? K Q1 Q2 over r², right? Or you can write it as 1 over 4 pi epsilon naught Q1 Q2 over r². What's the potential energy between them? Potential energy is just K Q Q1, Q2 over R. Okay? This is 1 over 4 pi epsilon naught times Q1, Q2 over R. So instead of R squared, it's just R. Let's plot that just so you'll remember. Potential energy versus distance. Let's say you have two protons, two positive charges. What happens to this function at very small r? When r is very small, becomes very large, potential energy approaches infinity. What happens when r approaches infinity? Approaches 0. So that's your potential energy function. Okay? Now let's interpret what this potential energy curve means. Okay? Let's say you have, let's say this is the total energy of your particle, your two particles. Okay? So total energy is constant, right? Now, when they're very far apart, okay, there's minimal interaction between them. They're hardly aware of each other's existence, right? So the total energy is all kinetic. There's no potential energy. What happens as they approach each other? As they get closer and closer, going this way, remember, is shorter distance, right? What happens? What's happening to the kinetic energy? This difference between potential and total is just the kinetic, right? So this gap between that I'm drawing with my double-headed arrows, that's just the kinetic energy. So what's happening to the kinetic energy? Decreasing. What does it mean when the kinetic energy is decreasing? That means they're slowing down, right? Why is that logical? Two protons, for example, two positive charges approaching each other, slowing down. Yeah, they repel each other. They slow down. Okay, so that's what this potential energy curve means. The potential is rising, your kinetic energy is dropping. So as they're approaching each other, they're slowing down. Kinetic energy is dropping. Okay? And eventually what happens? Kinetic energy becomes so small until such time when the kinetic energy goes to 0. So at this point, all your energy is just potential. And so what happens when they reach that point? They're still going to repel each other, right? So where's the force now? It's going to be directed that way, right? So if the force is directed that way, they're going to separate. And if they separate, what's going to happen? They're repelling each other. So they're going to try to speed up, speed up, speed up. Kinetic energy increases. Eventually what happens? They become so far away from each other that the kinetic energy levels off. So that's how you would interpret that potential energy curve. Okay? Now, let's relate that to the expression for, let's do that for a proton and an electron. What would the plot look like? This way. Oops. What happens? So this time around, I have a proton and an electron. So Q1, Q2, this whole expression is going to be negative, right? So what does that give you? When R is very large, what happens? Approaches 0. When R is very small, becomes very large but negative, right? So the plot of your potential energy is going to look like this. It's going to approach 0 as R approaches infinity, and it goes to a very large number as R approaches 0. Okay? So that's what your potential energy expression looks like. And that's what the curve looks like. And that's how you interpret. At very far distance, infinite distance, potential energy it's convenient to assume that as 0. Potential energy is 0 there because that's where there's minimal interaction between the two particles. Okay? Now, you don't have to set it to 0. You can set it to some constant value. Like I said, there's really no absolute scale for energy. What we're really interested in is changes in potential. The change in the potential energy is just the reverse of the change in the kinetic energy. So when you say the potential is dropping, potential energy is dropping, that means kinetic energy is increasing. The potential energy is rising, that means while that's happening, the kinetic energy is decreasing. All right, so what would be our expression for the kinetic energy, potential energy operator here? It's just going to be 1 over 4 pi epsilon naught. And what's the charge of an electron? Negative E, right? What is E? Negative 1.602 times 10 to the negative 19 coulombs. Okay, so that's the value of E. And that's why an electron volt, okay, if you accelerate an electron through a potential of 1 volt, 1 electron volt, if you remember, was 1.602 times 10 to the negative 19 joules, right? 1 coulomb volt is 1 joule. So that's just a good way to remember the conversion from electron volts to joules. So that's 1.602 times 10 to the negative 19 coulomb volt. Okay, so it's charge of an electron times 1 volt is 1 joule. I mean 1 electron volt, sorry. 1 coulomb volt is 1 joule. So our expression here is going to be, so from now on, this means charge of the electron, right? So that's negative E. That's the other electron's charge. Also negative E divided by distance between the 2 electrons, so R. Okay? And so, and then that is just a multiplicative operator. So if you operate that on a function, you just multiply the function by that. What's the expression for R? In terms of x, y, and z. If you want to do x, y, and z, normally you would use r theta and phi. It would probably be a better expression to use. But if you want to use r theta and phi, x, y, and z, what would r be? 2 points in space. What's the distance between them if you know x1, y1, z1? Let's just extend your Pythagorean theorem to 3 dimensions. So x1 minus x2 squared of x1 minus x2 squared plus y1 minus y2 squared. Your distance formula? Okay. Plus z1 minus z2 squared. Okay? All right. What is the complete expression for the operator corresponding to the potential energy due to Coulombic interaction? Coulombic interaction means electrostatic interactions, right? Okay, of electron 1 of helium atom with its nucleus. So you have a helium atom with a charge. What's the charge of the helium nucleus? How many protons in the nucleus? So the charge is plus 2e. For this nucleus, right? For the electron, so let's call this electron 1. What's the charge? Negative E. So what's our expression for potential energy operator? 1 over 4 pi epsilon naught. What's the charge of the electron? Negative E. What's the charge of the nucleus? Positive 2e over. You can just say, okay, let's just call that R1, the distance of electron 1 from the nucleus. And so that's, since we've written that as an operator, so we have to multiply whatever it's operating on by that expression. All right. The Hamiltonian operator is the total energy operator. So Hamiltonian operator H hat is just kinetic energy plus potential energy operator. And that's the definition of the Hamiltonian operator. So what would be the Hamiltonian operator for a hydrogen atom? Let's see. What do you have? What do you have in a hydrogen atom? You have a nucleus and you have an electron, right? So the total energy would be what? Energy total would be kinetic energy of the nucleus plus kinetic energy of the electron plus potential energy of the interaction between the nucleus and the electron. Okay, that's the total energy of any system of charged particles. Any system of particles, actually, in general, just kinetic energy of each one, add them all up, and then for each possible pairing of particles, you have a potential energy expression. Yes?
Should we not deal, is it always going to be dealt with the hydrogen atom?
No.
Or do you start inserting constants after?
Constants like what?
Or just
Okay. So let's write the Hamiltonian for this. So you have a kinetic energy operator for the nucleus, kinetic energy operator for the electron, and a potential energy operator for the interaction between the nucleus and the electron. So what was our expression for kinetic energy operator? Negative h bar squared over 2 times the mass of the nucleus, del squared for the nucleus, right? What's the expression for the kinetic energy of the electron? Somebody call it out for me. Alex? Negative, so this is the nucleus. Negative h bar squared over mass of the electron over 2 times the mass of the electron. Del squared, not delta. Del squared for the electron plus. Jonathan, what's the expression for the potential energy operator? No, negative h bar squared over 2 times the mass. That's for kinetic energy. 1 over 4 pi epsilon naught. What's the charge of your hydrogen nucleus? How many protons in a hydrogen nucleus? So the charge of the nucleus is plus E. Charge of the electron is negative E over R, the distance between them. Okay? So that's your total Hamiltonian operator. Now, if I wanted to write it in full, what would you have to do with this one? This would have to be written as what? A del squared operator is the sum of the second derivatives with respect to each coordinate. So this is partial derivative with respect to the x coordinate of the nucleus, right? Plus the second derivative with respect to the y coordinate of the nucleus, plus the second derivative with respect to the z coordinate of the nucleus. Okay, so may C, what's this del squared for the electron?
It would be, it should be the same thing.
Yeah, so call it out.
What's that called?
Second derivative
Second derivative. What about the third derivative?
with respect to,
X squared D.
okay, to the x coordinate of the electron, plus,
Second derivative with respect to y squared D.
okay, second derivative with respect to the y coordinate of the electron,
Second
the second derivative with respect to
z squared A.
z sub e, the z coordinate of the electron. Okay? So that is your expression for the Hamiltonian for the hydrogen. And R is, of course, just the distance between the nucleus and the electron.
That one that had multiple electrons, you just got to keep putting extra T.
Extra T's and extra B's. That's, I think that's the next example.
Okay,
Hydrogen
my
molecule. That was your
That
question?
was what I was trying to ask earlier.
Yeah. So H2 molecule. Let's look at H2 molecule. You have 2 nuclei, right? So to make a distinction, let's just call nucleus A, one nucleus A and the other one nucleus B. Okay, and so what's the charge of nucleus A? Plus E. What's the charge of nucleus B? It's also plus E. Each hydrogen atom has one proton in its nucleus. And since H2, you have two electrons, so you got electron 1, and let's put electron 2 over here. Doesn't really matter where you put it. Okay? So what's our Hamiltonian operator? Kinetic energy of each one. So call it out for me, Ashley. First one, kinetic energy of nucleus A, T hat A, plus kinetic energy of nucleus B, so TB hat, plus. We still have kinetic energies. We have two more particles. Kinetic energy of electron 1, so T hat 1, T1 hat. Kinetic energy of electron 2, hat, oops, hat, plus of so interaction between A and B. Oh, what did I do? Okay, right there. So VAB. So I'm just going to write that right now as V hat AB plus okay, so we're going to call interaction between electron 1 and electron 2. So I'm going to call that V hat 1, 2. Two more. All possible pairings of particles.
Potential energy of
A and electron 1.
Yeah. And then
Potential energy of interaction between A and electron 2. Oh, that's two more. So 2. Another 2 would be what? B and electron 1 plus potential energy of interaction of B and electron 2. Huh? Yeah. You can see how it can get really here. But what we really do is we do a lot of simplifications, and you don't really do it this way for like a collection, a large collection, like a mole of particles, because that's impossible. So what you do is you would solve it for a single H2 molecule, and then you apply statistical mechanics. So you do statistical averaging for to get properties like pressure and temperature. So that's a different subject. That's we can get to that after thermodynamics. Okay, so we're looking at just little particles for now. Okay, so let's see. What would be the expression for T hat B? Bang. Negative over 2 times the mass of B, which is just the mass of the nucleus, right? Mass of B times del squared for B. What would this expression be, Chow? B hat 8. 1 over 4 pi epsilon naught times the charge of B, which is, what's the charge of B? A. What's the charge of A? This is A2, right? Positive E. That's 1 proton in the nucleus. Charge of electron 2, negative E, divided by the distance between nucleus A and particle 2. So this distance right here is RA2. Call that RA2, and that's what you write over here, RA2. Okay, so that's how you construct the Hamiltonian operator. You have a kinetic energy operator and a potential energy operator.